Hello, this is local illumination, video 1, so we're talking about the pixel shader here. So the normal vector is a vector that is perpendicular to the surface at a given point. So I wanted to show how normals are interpolated to create a smoothness effect on the rendered object. As you can see, it seems smooth. You can't really see the edges of the object. However, if I add a modifier to specify not to interpolate the normal vectors of the faces, you can clearly see the edges, and this is how we achieve flat shading. There is no interpolation between them. So ambient light is the light that kind of just exists in the whole world. They give the objects their base color pretty much. It is just straight up defined in the material under diffuse albedo, give it a nice color. And in the pixel shader, this essentially becomes the basis of the final pixel color that we will then add on the spec albedo and adjust it by the light strength. This could be swapped out for a texture for more realism, but in this case we're just looking at the color. While it is called diffuse, the diffuse part comes on when you multiply it by the light strength, which is first adjusted according to Lambert's cosine law and then passed to the method. So it technically only becomes the diffuse light once you multiply it by the light strength. An object which emits diffuse reflection is said to have Lambertian reflectance in accordance with Lambert's cosine law. This law states that the surface luminance is directly proportional to the cosine of angle theta made by the unit vector from the surface to the light source and the surface normal. Next we've got specular reflection, which are the tiny bright highlights on a given shiny surface. First, let's talk about the Fresnel equations. Now this equation attempts to approximate the amount of specular light that is reflected into the eye based on the angle made by the light vector and the half vector. It is implemented by passing in the Fresnel value, which are the values when this angle is 0, which is the ideal reflection, the half vector, and of course the light vector. This is the vector going from the point on the surface back to the light source. The formula we just looked at is implemented here. Next we've got the roughness factor, which is the result of the microfacet model. The tiny bumps on the surface, you can't really see them, but obviously shinier things have less of them. Now this is where the specular exponent and the smoothness scalar value n come into use. The distribution model is obviously just an approximation of reality, so we use some magic constants. This one is based on a different angle, we'll call it theta I here. In the Blinn-Phong shading model, this is the dot product of the half vector and the normal vector. As you can see, it is implemented here. However, I want to show you a different shading, which is just the Phong shading model, in which case we need a reflection vector, which is the reflection of the incoming ray. And in this case, the dot product is between the reflection vector and 2D eye vector. Once we've got these values, we just multiply them together. In the end, obviously scale it down to the range we are working with, the GPU light's unit vectors. Add the specular light onto the ambient light and then multiply it by the light strength to get the final pixel color. So to demonstrate how the material parameters work, I created a new branch and changed a bunch of values randomly, and we can see the difference. So obviously on the master, this is the original Blinn-Phong shading model with the original material parameters. This is what it looks like, and with the funky colors, it's just different a little bit. You can see the difference. Over here in the different shading, I just call it different shading. Obviously this is just the Phong shading model. This is what the Phong looks like on its own. On the left we've got the Blinn-Phong shading model with larger highlights and smoother fall-offs, while on the right we've just got the Phong shading model, smaller, more crisp highlights. Now this is with all the same material parameters, hence you can see that the Blinn-Phong is a more realistic shaded model. Finally, directional light. Essentially the sun, all the light rays are parallel, so we don't really care where in the world the light source is located because all the light rays are going the exact same way, same strength, same intensity. As you can see, the directional light uses only the strength parameter and the direction. So we can't get a vector from the surface to the light source because it doesn't matter. We can just simply negate the direction of the light vector. which is what we achieve with this.